Welcome. We are into the third part and eventually the last part of the SPARQL Algebra topic. So in the last lecture, we have talked about how we can translate or transform one abstract syntax tree corresponding to a query into its corresponding algebraic form. And the task we are remaining with is how to evaluate one algebraic representation of a query with respect to a graph or one RDF knowledge. So that will be precisely the topic of our discussion, right? So as we have already discussed that we had made use of few algebraic expressions, the operators. So the operators are BGP, which is the basic graph pattern. It is just basically to evaluate any given simple pattern, right? So it is a kind of triple pattern we are talking about. Then we have talked about joining two solutions. This M1 and M2 are two solutions, and we are doing a conjunctive join of these two solutions, right? And as we go forward, we'll try to see what we really mean by conjunctive join of two, right? Now, left join we used for, so this is what we used for joining two group graph patterns, right? Group graph pattern. Now, left join we use to represent, so this is the algebraic operator corresponding to optional graph pattern, right? Optional graph pattern, right? And we know that there are two cases. One is this optional graph pattern may contain one filter in the second part of the patterns. So, for example, you have say BGP1, then optional, then BGP2, right? Now, it might so happen this BGP2 might contain one thing. So, if it does contain one filter, so that will be used to test whether the given these two solutions, if they are joined with using this left join operator, whether we need to impose any filter condition, right? Now, if we do not have a filter constraint here in BGP2, then it will always be taken to be true. So, this is what we have done in the last lecture, right? And you have got a filter operator, which is basically representing the filter keyword, right? Filter corresponding one constraint, which is f. So, basically you are applying a filter constraint over a solution, right? And finally, you have one identity of join. So, this Z is the identity of join, identity of the join. If you join something with Z, you will get the same thing, right? So, it is basically an empty pattern or an empty sheet, right? So, these are the operators that we have talked about, and we have seen that how we can transform one abstract syntax tree into an algebraic form using this set of operators, right? Now we'll try to provide formal definitions of these algebraic expressions, because these informal definitions really do not tell us really how to evaluate one algebraic expression, right? So we need to have formal or mathematical definition of these operators, right? So if we have these mathematical definitions, then perhaps we can evaluate properly or precisely one algebraic expression. So that is the kind of thing we'll be doing, right? Now, as we are talking about a formal definition, right? So we are talking about the formal definition of the algebraic operators. So for that, we will be using some terminology, so the definition to define them, right? So the first thing that we like to define is a solution set. So it is basically you have as an output of the query, you have a list, right? So you are having a list, right? And what you have in the list, in this list, so you are getting a kind of tabular form. So, and what you have in the tabular form, you have different variables in the columns, So basically the variables that you are projecting, right? And for each variable in a row, you have some values, right? In row 2, you have another value. So this solution sequence represents the sequence of this solution. So individual rows, you can see they are the individual solutions that you are getting out of evaluating the query against a graph, right? So each row represents a solution, right? And the sequence of it is the solutions. Now coming to individual solution. The individual solution is a single row. We are representing this individual solution as mu, right? And what is mu? Mu is basically a function. What it does, it maps the set of the variables to the RDF term, right? So you see in a row what we have, for every variable you have a value, and this value is belonging to the set RDF term, and we have already defined what is an RDF term, which is basically a union of, to recall, this is equivalent to the union of IRI set with the set of the internationalized resource identifier, or the URIs you can say for the sake of simplicity, union RDFT. So you can have say RDF blank note, and you can have some other thing, right? So you have so basically whatever terms you can say, they are part of this RDF term, right? So basically what exactly you are doing here, you are instantiating every variable to its corresponding uh, mm, value, right? And that kind of mapping is being done by this solution function mu. And you can see that you have this space of variable v, which is the set of v, and this is the set of RDF term, right? Now this mu, which maps one element of v to RDF t, is basically a partial function. This is a partial function. Why is that? Because of the very fact that you may not have one mapping for every variable in RTF, right? So that's why it is one partial function. Now, what do you mean by a solution? So, when we talk about the solution is what? Solution, as we have mentioned, that solution is a instantiation of all the variables that you can have, right? So if you have say v1, v2 to vn as your variables, so they are the object which you are trying to instance, right? And together assignment of these will give you a solution, right? We are mapping individual variables to the corresponding uh, value, right? So basically, uh, if you consider a particular pattern which is P, and we are trying to evaluate BGPP, and we are trying to define the solution mu for this BGP. So we are now restricting ourselves to this algebraic operation, which is the simplest algebraic operation, BGPP, right? So in that case, you need to define the domain of this mu, right? So domain is again a set from which this mu will be taking value, right? And what is what that set would be? That set would be basically the variables that are present in this mu, right? So the domain of mu would be basically the variables that are appearing in P, right? So this is exactly we are saying here. The domain of mu is the set of variables that appears in P, right? So, and the second thing is that it is not always true that you have only variables and concrete terms. you can have also blank notes in your pattern, right? Now, if you have blank notes, then these blank notes, they are kind of anonymous notes. You know that already. So these are anonymous nodes. Now, as they are anonymous nodes, they can be instantiated with different resources or values. So they are like variables, not exactly the variable. To give you an example of this, so for example, you have one actor A1 who acts in a movie, right? Right? And there is another actor A2 who acts in another movie, acted in another movie. Now, you want to find whether they are co-actors or not, right? Now, how do you write this pattern? The pattern would be written like A1, say, if I say acts in, right? So, it will be writing like this, A acts in, then you have a forward slash. We are writing a path pattern here. A forward slash, and you have the reverse of acts in and then A2, right? So if you have this, you see that this M1 is becoming to be a blank node. I really don't care what it is really. Even if they act in two different movies, so this is M1 and it may be say M2, they will be declared as co-actors, right? So the point that I'm trying to make is this is a kind of blank node, right? This is a kind of blank node. So let us represent this as X, right? Now these can be instantiated by M1 and M2, right? And with respect to that, you can see that I am getting two entries in my solution with A1 and A2. So this A1 and A2, they are getting repeated, right? So also you can have say A3 and A4, they can be connected via another means, right? So again, you can instantiate this blank node with some other value, say M3, right? So what my point of concern is that these blank nodes, they should also be treated as variables because they are kind of floating things. They are kind of blank or templates. So you have to fill in some values there, right? And depending on how you are filling the values there, then you will be getting different solutions, right? So we are defining these as some assignment, right? So this for this variable, while we are giving some values to the variable, we are binding some values to the variable. We call them as instantiation. We are instantiating one variable with a value. Now, whenever we are assigning some values to the blank nodes, with concrete values to the blank node, we call that as assignment, right? Now, this mu would be applied over after we have done possible assignment, right? Now, this mu would be a solution for this P if you have done the assignment over the P by replacing these blank nodes with some other values, and then whatever is left with, if you do some instantiation over the way. Now let me clearly say which part is assignment here and which part is so here we are basically doing the assignment, and in this part we are doing the instantiation, right? Now if we do both these things and if we see that the structure that we get out of this assignment followed by instantiation is a subgraph of G, then we say that mu is a solution of BGP, right? Or I'll not say capital GP because this is operator. So I should write P small g small p, right? So this is how we can define a solution, right? Now the next thing, as we have mentioned in the last example, that a particular two nodes, like say A1, let me draw it 1 second. A1 and A2, they can be connected via say one blank, right? Now they can, if as you are doing multiple instantiation of this X with say movie1 and movie2, so we'll be repeating this A1, A2 and A1, A2 in your solutions. So this assignment, this result of assignment of this blank node with M1 and then M2 is giving you two solutions, two same solution, right? The solution is getting repeated here, right? So that brings us to the concern that a solution can be repeated and there would be multiple instances of the same solution in the result, and that is what we call as the multiplicity of the solution, and that depends on the number of different assignments you can do, and then you get a subgraph which is a you get a graph which is a subgraph of the original data or the graph which we are trying to query, right? So as many number of different assignments you can have, that many solutions, that many repetitions of the same solutions will be having, and that thing is called the multiplicity of the solution, right? Now the basic thing which is really the evaluation of the BGP. We not need to talk about the evaluation of the other patterns, other algebraic operators, but the simplest thing or the most fundamental thing is the evaluation of the BGP. Now evaluation of any algebraic expression, so let me try to put forward the convention. So any algebraic, so this A is one algebraic expression or algebraic object, right? So let me write it down. It is one algebra object, or algebra expression, you can say, right? And what we are doing, we are trying to evaluate this algebra object with respect to one graph, which is basically the graph you are querying, right? So this is what we call as evaluation of A on G. So we are evaluating this algebra object over on the graph G, right? So similarly, if we say BGP PG, it means it is the kind of result of evaluating BGP P over G, right? Now it is imperative to say that this would be a multiset of the solution, right? So why it is a multiset? Because we are getting a set of solutions like mu1, mu2 to mu n, and these individual mu's are basically the individual rows in your output stream, right? And as we have seen in the last slide, that a solution can be repeating, right? So you can have multiple instances of mu1 in this set, right? So this mu1 will be coming with so for example count n1, mu2 will be coming with count n2, mu n, I should be using different notation. So mu1 comes with say x, okay, say m1, mu2 comes with m2, and mu-n comes with say mn. Some of them can be 1, right? But others, they can be more than 1. So as this set is kind of having elements that are repeating, that's why it's called a multiset, right? So we'll be using a multiset notation. Let me talk about the notation that we are going to use to represent a multiset. Now, this is how we will be representing a multiset. We will be representing a multiset as a set. We are defining a multiset over a set. So this is the original set, and we are converting to this is a multiset, and we are representing this into with this kind of set theoretic notation. And what we are keeping here, we are keeping here the element. So this is one element from S. So this S, the small s, belong to the capital S, which is the original set. and along with that we are keeping the count of s, the number of repetitions of s in small s in the set, original set. And this function is basically talking about the count of small s in capital S, right? And this function, this particular thing is called the multiplicity of uh, a particular solution or entry in a multiset, right? Now let us come up with some examples, illustrate the concept that we have earlier. So here we are having what this is a single graph, though they are not entirely connected, but this is a single graph. So this is my G, right? Now you have Christian Bale stars in something which is a type movie and the title mechanic, machinist. You have another entity like Morgan Freeman who starred in something which is a movie, and the title of that is Bruce Almighty, right? Now with this, let us try to think about evaluating this BGP. So this, whatever you are seeing inside is the P, right? What you have inside this, actor starts in a blank note, and a blank note has got title movie. So basically, this kind of structure we are trying to align with, right? Now, what kind of solutions we can have? So this can be one solution, like you instantiate actor with Christian Bale. We are instantiating this variable actor with Christian Bale from this, right? And movie with the machinist, right? And we are assigning uh, underscore a to underscore x, right? So this is an assignment we are doing on the blank note by in order to align our pattern with this part of the graph, right? So what would be the other solution? The other solution would be you have actor, you are assigning, you are instantiating actor variable with Morgan Freeman and instantiating movie variable with Bruce Almighty and assigning this blank note B to blank note X, right? So you see that you have only one assignment for every solution, right? So as you are having only one assignment for every solution, so that means you have multiplicity for this solution to be 1, and the multiplicity for this solution would be also 1. So this is a case where you have got two solutions, but each one of them is having a multiplicity of 1, right? Let us take another case. So this is another graph where Christian Bale stars in A, and A is a movie having titled The Fighter and stars in something is type of movie. The title is American Hustle, right? Now let us assume that this is our pattern, right? Now with this pattern, let us see what kind of solutions we can get, right? So this here we have a solution. So we are having one variable here, right? And we are instantiating that variable with the value Christian Bale, right? But this blank nodes, you have got two blank nodes and you can assign two values, right? You can assign A to X and Y to the fighter. So this is one solution, right? What can be another solution? We are having the same instantiation. We are instantiating the actor variable with Christian Bale, but we are having a different assignment. We are assigning B to X and the American Hustle to Y. So you are seeing that though we have a single solution, but we are having two assignments. So we have one solution and two assignments. We are having two assignments, right? So as we are having two assignments, where we will be having a repetition of this solution twice, right? So this is a case where you have one solution with multiplicity right? Now, the next important definition that I like to discuss is the compatibility of two solutions, and this is pretty much required in many operators. Whenever we will be defining many operators, this compatibility will be playing a very huge role, right? So, what is compatibility? So, let's say you have two solutions, right? So, you have M1 and M2. These are the two solutions. And let's say you have say V1 and V2, then you have say V5 as your variables in. So these are the domain of your solution in M1, right? And in M2, what you have? You have say V1, V2, then you have say V6, right? Now, let us assume that we have a solution here V1, which is having say x1 to be value here, x2 to be value here, and x5 to be value here. And mu2 here we are having say x1, x2, and say x6, right? Now we'll say that these two solutions are compatible if for the variable which are common to both the solutions, the variables which are common to both the solutions, they are assuming the same value. They are instantiated with the same value. So, for example, here V1 has been instantiated with x1, V1 has been instantiated with x1 here. V2 has been instantiated with x2, V2 has been instantiated with x2 here. But I really don't care about the case where V5 and V6 are two different variables. So these are not common to these two solutions. So we will not be bothering about them. We'll be bothered about the case where we have got common variables, right? And this will be very much useful when we talk about the join operator. So let me define this compatibility of the solution in formal terms. So we'll define the intersection of the domain of mu1 and mu2. So in this case, what would be the intersection of domain of mu1 and mu2? It will be v1 and v2, right? So this will be the result of intersection of domain of mu1 and domain of mu2. Domain of mu1 would be v1, v2, v5, and domain of mu2 would be v1, v2, v6. And if you take intersection, you will be having v1 and v5. Now, if you have this for all, so whatever element, so this is a set you are getting, right? So whatever element, whatever variable you can draw from here, the value that you have for mu1 for that variable, that should be equal to the value that that particular variable would have for the solution 2. And that should happen for all the x's that are appearing in the intersection of domain of mu1 and domain of. So then we say this mu1 and mu2, which are two solutions, they are compatible, right? Now let us take an example and I'll try to clarify the thing a bit more, right? So there are three cases, so three pairs of solutions. So here we are having mu1 to be, here we are having two variables, x and y. We are instantiating x with a and instantiating y with b. And in mu2, we are instantiating y with b and z with c, right? Now, first we'll compute the intersection of domain of mu1 and the intersection of domain of mu2. What would it be? It will be basically only you will be having y, right? And you can see that for y, we have b to be the value instantiated to y in both the cases. And we will not really care about what value has been instantiated to x and what value has been instantiated to y. So by our definition, this is a compatible solution. So this is compatible. Right. Now let us take these two pairs, right? So what would be the intersection of domain of mu1 and domain of mu? So what would it be? So basically we have x, right? So x is the common variable in this solution, in these two solutions, right? But you can see that x had been instantiated with a in mu1, but in mu2 x has been instantiated with b. So in that case we say this is not compatible. So this particular uh, thing, this particular solution is not compatible, right? Now coming to the third one. So this is another different case, right? So here you can see let us compute the domain of mu1 intersection domain of mu2, right? And of course needless to say it will be a null set, right? Now if you do not have anything in common, so you don't need to care about whether they are having same values or not. So by that logic it will be compatible. So I don't care about the things that are not common. So these x and y, they are not common to mu1 and mu2. So this is compatible, right? So you see we have a very formal definition of why or what we mean by compatibility of two solutions, whether these two solutions can go with each other. So the simplest way to talk about this, whether these two solutions go with each other. So this is what I'm trying to make for last few minutes. So whether two solutions go with each other, right? Now let us define the union of two compatible solutions. So we assume that this mu1 and mu2, they are compatible, right? Now with this assumption, let us try to define what is the union of this, and it is very simple to follow. Basically we are uh, including the all the kind of instantiation you can have either in mu1 and mu2, right? And this is easy to. Now with these definitions, let us take one example, and as we go through different constructs like say join and left join and others, we will be using this example. First we will be defining the operators formally, and we will be taking this particular example and try to illustrate this example uh, uh, with different operations, right? So we'll be applying different operations over this example and try to see whether our formal definition goes with the output, right? So this is the graph. You can see that you have three entities: Rabindranath Tagore, William Shakespeare, and Paulo Coelho, right? And they are all type of writers, and Rabindranath Tagore has got two representation in his name, Rabindranath Tagore in English and Rabindranath Thakur in Hindi, and William Shakespeare has got the label to William Shakespeare, and we do not have the language annotation here. And Paulo Coelho has got year of birth to be 1947, and Rabindranath Tagore has got year of birth to be 1861. Now, in some examples, we'll be modifying this data a little bit, but I'll talk about that modification later. Right. So let us look at the data turtle representation of this graph, right? So we are going to see the turtle representation of the graph that we have just seen, right? So you have three entities: Rabindranath Tagore, William Shakespeare, and Paulo Coelho, right? And we represented all the kind of relations that we have. with one exception. You can see that this EXS name Paulo Coelho was not there in the graph, so you have included here, but you can include it or not depending on the examples that will be showing, right? Now with this, let us move to the definition of the uh, operators. So the first operator that I like to describe is the filter operation. First, let us apply the filter operation over some result set. Then we'll be defining it formally, right? Now, while we will be describing the illustration, so you can see that in the bottom part, you will be having the input solution sets. So this is one solution set, and we know that we represent solution sets with M, right? Now, if you have multiple solution sets, we'll be naming them as M1, M2, M3, and so. So this is your input solution set, and I'd like to remind you that it might not be a triple kind of thing. So it depends on how you have written the select clause, and I guess the output, the query that has given this output, this table as output, has got v and name in the select clause, right? So basically, the query that produced this has got this in the select clause, right? And there might be certain conditions by which the query has retrieved these values from the data that we have seen earlier. Now this would be the operator. So here we'll be representing the operator, the middle box, and the top box will be representing the outcome or evaluation of operator, right? So what you can think of this was, so you have represented the SPARQL query in as one algebraic object, right? Now we are evaluating this algebraic object over G, right? So you have one input G, input graph, right? And after this evaluation, you are applying this filter F over A, right? And whatever you are getting here is basically the so basically the evaluation of F A over, right? So this is what we are getting. Now how do we define this filter formally? So let us first represent what we mean by the evaluation of a filter, right? So we have already seen the notation we have used to represent the evaluation of some algebraic object, right? So basically you have filter, right, f a t. So this is what, this is basically the result of evaluating this filter f a over t with filter f and algebra object a, right? Now how do you define so it would be a multiset, the outcome would be a multiset. So this is what we have agreed upon. So evaluation of every algebraic expression would be would result in one multiset, right? So we'll be defining this as a multiset. So this filter f a t it would be a set, but it will be a multiset, and we know that how to represent multiset. It will be a solution, then the multiplicity, right? And this, now let us assume that this M is the result of evaluation of A over G, right? Now this mu should belong to M in the first place, and the multiplicity of this solution should be greater than 0, otherwise it will not be appearing in your result set. And you want this filter condition to be satisfied in this solution, right? So we represent that like this. So you have this mu, and you evaluate this filter condition over this mu. Given this graph, it will become to be true. In that case, you will be putting this mu in the solution set for this filter, right? And what is this mu? Basically, this mu f t is basically the result of the Boolean result. So it will be a Boolean result. It will be a Boolean result of evaluating filter constraint or condition f over mu, right? So this is how we can define a filter operator, right? Now coming to the next operator, which is join, right? So what you have in join, you have to have two solution set. So you have one solution set M1, the other solution set M2, right? And what would be the output of this? So let us look at the solution set. So you have got William Shakespeare, and the name is William Shakespeare. Rabindranath Tagore has got two entries because Rabindranath Tagore has got English representation of the name and Hindi representation. And in the other table, other solution set, what you have, the V to be Paulo Coelho, and you do not have name in Paulo Coelho, and the birth year is like say 1947, right? And you have Rabindranath Tagore here, Rabindranath Tagore in English, and 1961. So what would be the result of evaluation of join? So basically you see, first you look at the compatible solution, right? Let us look at this solution, William Shakespeare and William Shakespeare. Is it compatible? So let us try to find out whether you have the value for V, and we find out a solution here in M2 which has got William Shakespeare for V and William Shakespeare string for name. We do not have any, so this is not compatible. Now as this is not compatible, it will not be coming in the result of join, right? Now coming to this solution. So for V we have got the URI Rabindranath Tagore. Now try to find V. Yes, we have Rabindranath Tagore in V. Now in name we have got Rabindranath Tagore string with English annotation. We have in name we have got Rabindranath Tagore string with English annotation, right? And as we have got the values for V1 and name to be same for this solution, so this is your now mu1 and this is your mu2. So these mu1 and mu2, or I should represent it in a generic way, right? So I should write this to be say mu I and mu j, and this mu y and mu j, they are compatible. As they are compatible, they will be going to our solution set, which is basically representing the evaluation result of join, right? So in the join we are taking this V and name, and we are also taking the other kind of thing that we are having here. Also we would have taken something which is here but not here, right? So it is joining based on some common values of the different variables which are appearing in both the tables, but also taking into account the values of the columns which are not present in either of these tables, right? So this is the result of the join, right? Now let us try to define this formula, right? So first let us assume, as we are having two uh, uh, mm, solution sets which we are joining. So we have two arguments, which is a1. So this is the first algebraic object in this join function operator, and this a2 is the second algebraic object. So let us try to represent m1 to be equal to the result of evaluation of a1 against g, and m2 to be the result of evaluation of a2 against e, right? Now we need to find out the solutions that are compatible, right? So we take one solution which is mu I from the first solution set, which is m1, and take another uh, solution from the m2, which is mu j. So we take a pair, one from one m1, other from m2, right? So this will be our candidate for join, right? And what is the condition? Of course, this this mu1 or mu y should belong to m1, and mu j should belong to m2, and of course you need to ensure that the multiplicity of mu I with respect to this m1 should be greater than 0, as this is, if it is not 0, it cannot come into the join operation, right? Similarly, the multiplicity of mu j in m2 should be greater than 0, right? And the most important thing is that mu1 and mu2 should be compatible or are compatible, are compatible, right? In that case, we will take a solution. So basically uh, mm, this mu, the final solution would be the union of mu1 and mu2, right? The final solution would be the mu1 and mu2. So this mu is basically a combination of a pair of these two, and if you take the union, that will be giving you the final compatible joint solution, right? So this particular set, let us name it to be say, as we are talking about join, calligraphic join. So join me, right? This join me is basically all the pair of solutions, one from m1 and other from m2, that are compatible. So the simplest way to say the thing. Now with this, let us define the join evaluation result of the join, right? So what we have, yeah. So you have evaluation of join a1, a2 with respect to a graph G, right? Now this should be, again, it will be a multiset, right? And how do we represent multiset? Mu n, right? And here we will be defining what would be the value of n. So what would be the value of n? So basically, if you go back to the last slide, so here you have Rabindranath Tagore once and Rabindranath Tagore once. So, and how many times you are getting this Rabindranath Tagore as entry here? 1, right? Now let us assume for the sake of simplicity that this Rabindranath Tagore and Rabindranath Tagore En is repeated here. So we can have repetition. So for example, you have something like Rabindranath Tagore underscore Tagore. I'm not writing it properly perhaps. And here we have got the same thing. Rabindranath Tagore, then followed by En. Basically, we are repeating this entity. Now here this multiplicity of mu1 is 2, right? Mu I is 2. But here the multiplicity of mu j is 1. So in that case, we would have a repetition here. So we would have a repetition of this same solution here, right? Because of the fact that we are taking a kind of product of these two solutions with this solution, right? So the multiplicity of the output would be 2 multiply 1, which is 2. So if we had a situation like this, we would have got a, kind of two number of solutions here, right? So we will be doing the same thing here, right? So here the n value of n would be, so if you have 1 mu, so we are counting the total number of things, right? The total number of entries, right? So it will be, so what would be your mu now? So your mu is basically the union of all the pairs that you can get. So it will be union of all the pairs you can get. So this mu is that one, right? Now what would be your n? So we'll be taking each pair, right? So you take mu I and mu j, and this belongs to j mu, right? And you will take the multiplicity of mu I from the first solution set and multiply that with the multiplicity of the second solution or the jth solution from the second solution, right? So this will be the total multiplicity of this solution, right? And of course this should be greater than. So this is the definition or mathematical definition of the join, right? Now with this, let us go to the terminal and try to see some interesting observation that might not go with what we have discussed now, right? So let us go to the notepad to see another kind of data set. So what we have, so this is your 16 where EX016, where you are having information about Rabindranath Tagore, William Shakespeare and Paulo Coelho. Now we have got another data set which is EX017 TTL, right? Here we have got information about Salman Rushdie, then Agatha Christie, then Rabindranath Tagore, then Paulo Coelho. Here you see the name part is omitted. Let me remove this here from here, right? So the name part is removed, right? Now let us try to see what we are doing in this query. So here we have defined this EX016 to be the from node, and we have defined EX017 to be the name node. And here we are having two group graph patterns. So this is one group graph pattern. Here we are extracting, let me put this value somewhere else so that we can make it. So we had got, let me take it out again. We'll be using this later. We are commenting this and let us call it to be for loop. Right. Now let us go back to the query. So this is a group graph pattern where we are just extracting the names of different entities, right? Now this is again another group graph pattern, and inside that we have a graph pattern. So why we have done that? So we are trying to get here. So here let us look at what we have inside. Then we'll talk about why we are doing the graph. So we are extracting the birth year of some entity, and optionally if they have names, then we are trying to extract the names, right? Now here, if we see the data, here we don't have the name information of Paulo Coelho, right? Now, but we have got the year of birth info. In that case, Paulo Coelho will be one output, will be coming to the output stream for this query, right? And we are using graph, and we have used the named representation of EX00017. So that means only the triples from EX017 will be participating in matching this, right? But the triples from this will not be coming here, right? And this I have done with a purpose. The purpose is, so let me first look at what kind of output we can get for each of these group graph pattern. Let me remove this part, right? So if we remove this part, we are just left with the group graph pattern 1, right? I want to see what kind of output we'll be getting, right? So let me execute 017, right? So I'm trying to execute 017. So you can see that we the result is we are having the V, the name, and the birth year, right? Now, so as we do not have the birth year, so if you go back to the query again, um, if we go back to the query again, so we do not have any birth year value, so that value will not be there. So we do not have any value in this table, right? Or maybe we can put it, we can put it off for this query. So we just put it off, right? So let me execute the query again, right? Now let me go back to the slide and go to yes. So here we are trying to simulate this, right? So you see we have this table M1. We are trying to simulate this, but we want Paulo Coelho as well to be here, and that is exactly we can see we have in our terminal as result. Let me go back to the terminal. So you can see that we have got the exact same result, and added to that we have got Paulo Coelho and with a name value, right? Now let us change the query to see what we have in the second pattern, right? So we'll be commenting this out. So we are going to the data, we're commenting this out, and we are bringing back this birth year because we know that we have this in the second table, and bring back the second group graph pattern, right? Now let us see what would be the result of executing the same query on this, the query on the same data. So we execute this query again because we have changed it a little bit. Now you see that Paulo Coelho is also appearing here, right? But you do not have anything on the name against the name variable. So we have a condition here in, so this is your M1, right? And this is your M2. Now in M1 you focus on the solution Paulo Coelho. So In this solution, V is instantiated with the value Paulo Coelho, and in M2, V is also instantiated with Paulo Coelho, right? Now, name in M1 has been instantiated with the string Paulo Coelho, but name in the second table or second solution set is not instantiated with anything. So that means name for this particular solution, the Paulo Coelho solution, is not bound. The name variable for this particular solution is not bound, right? So as per the definition that we have given for compatibility, so these two solutions, this Paulo Coelho row from this table 1 and Paulo Coelho row from the table 2, they are not looking like compatible, right? Now let us look at the join operation. So let me get back to the query, revise that query. So the revision would be just to put the group graph 1 back again, right? So you see that we have brought back the uh, uh, group graph query pattern in query, right? So basically we have G1 and this is your G2. We'll be doing a join of these two results. So this will be giving you the solution set 1, that is table 1, and this part will give you the solution set 2, that is M2, right? Now let us fire the join operation, right? So we execute the query again. So you see that Paulo Coelho, though it looked like to be not compatible, is coming here, right? So we should consider that if we have some variable which is not bound, so that will also be treated to be playing part in compatibility. So you have a compatibility here in the first row. So if we have a compatibility, yeah, in the first variable V, right? But in second variable, that is name, in first table this name has been instantiated, but in name 2 it is not been instantiated. So in that case, we'll treat these also to be bound or compatible, and as they are compatible, we are taking this to be the result of the join. And as we had 1947 here, we will be having this 1947 here. So this is a little caveat you need to consider when you talk about compatibility of the solution, right? Now we have defined the join operation. So let us talk about the example that will illustrate more about how do we compute the multiplicity of the joint solution. So let us take the example like you have M1. In M1 we have got two solutions, right? So mu1 in mu1, x has been instantiated with A and y has been instantiated with B, and you have mu2 which has been where x has been instantiated with A, but y has not been instantiated with anything, and the multiplicity of the first solution mu1 is 2 and the multiplicity of the second solution, that is mu2, is 1. Now we have got another solution set where you have only one solution, which is mu3 with instantiation of y with B and instantiation of z with C, and it has got the multiplicity of 3, right? Now whenever we talk about join, we need to compute J, right? J mu, and J mu is basically the set of compatible pairs, right? Now we take mu1 and mu3, right? We will be taking one from M1 and one other from M2. Now there are only two possibilities. We can take mu1 mu3 and mu2 mu3. Now let us take mu1 mu3. So if we take mu1 mu3, so we have got x to be instantiated with A, y to be instantiated with B, and here y is instantiated with B and z is instantiated with C. So you see that we have a common variable in the domain intersection of the domain of mu1 and the intersection of domain of mu3, and this is instantiated with B. So these two are compatible. So this will be included in my set of mu, right? And what else is there? Let us check this one. So this mu2 and mu3. So let us see whether mu2 and mu3 can be one possible candidate to be included in J mu, right? Now you have got x to be instantiated with exa. We don't have any x here in mu3, so that means these two are compatible. So we can include mu2 and mu3, right? Now what we have got three solutions: mu1, mu2, and mu3. And what would be your mu? Mu will be basically mu1 union mu2 1 union mu3, right? So basically it will be x to a to x. You are instantiating x with a, instantiating b with b to y, and c to z. So this is your mu. Now what would be the multiplicity? The multiplicity would be very simple to follow. So basically, what is the multiplicity of mu1? 2, right? What is the multiplicity of mu2? Is 1. This plus what is the multiplicity of uh, uh, okay, so yeah, no. So the multiplicity, we are talking about mu1, mu3, right? So here it will give you the multiplicity of 2 multiply the multiplicity of mu3, that is 3, which is 6. Now coming to mu2 and mu3, right? So what multiplicity will be getting here? Basically the multiplicity of mu1, mu2 multiply the multiplicity of mu3, which is 3. So 3, and we'll add up these two, basically 9. So the multiplicity of the final solution would be 9, right? Now coming to union, again union takes two algebraic operators as argument, expressions as argument, a1 and a2, right? And union is very easy to follow. Basically you are adding this row here without checking whether it is compatible with the things or not, right? We are just adding them the solution, right? So how do we define the formal definition of this union? So again we'll be taking this M1 to be A1 G and M2 would be A2 of G, right? So what is the result of evaluating one union operator? So you have got two input algebraic expressions, A1 and A2, and this would be basically, again it will be a multiset, a solution, and multiplicity, right? So here you have this mu, this should either belong to M1 or belong to, right? So either mu belongs to M1 or mu belongs to M2, right? And what would be the multiplicity? We are just adding two tables, right? We are just appending one table with the other table. So the multiplicity will just be added, right? So it will be mu, the multiplicity of mu in x1 plus the multiplicity of mu in x2, and of course this should be greater than, right? So this is how we define the union, evaluation of the union operator. Now coming to the next operator, which is left join, and we know that left join has got two flavors. One is left join without filter and left join with filter. So let us talk about the case of left join without filter. So basically whatever you have in the left hand side, they will be coming here, right? So you see that we have got William Shakespeare row, this is happening here. Rabindranath Tagore in English row, it is happening here. Rabindranath Tagore Then mm, Rabindranath Tagore Hindi name, it is also coming here, right? William Shakespeare we have already considered, and Paulo Coelho who is already there, right? And along with that, whichever variable is getting compatible with the first one, the left one. So basically, Paulo Coelho and Rabindranath Tagore, they are getting compatible, right? And for them, we'll be taking this value of this B here and putting in their respective cells, right? So Paulo Coelho is compatible with Paulo Coelho for V. So 1947 will be appearing here, right? And 1861 will be appearing in both the cases, right? So this is the result of left join. So guys, we can check this out by running this query in the terminal, right? So let me check the files again. So uh, we'll be using, I guess, the graph ex016. Okay. Uh, so yeah, so we have got. So this is the query, right? So we have got the left join, simple left join, but we will be using this query to do something else. We have got a filter here. So as I have mentioned earlier that this left join can come with a filter in the second part of the optional, or it may not come with a filter. So we are talking about the simple left join operation. So there we say that we do not have a filter. So I'm just commenting this filter out. And let us see what would be the result, right? So let me move to the command prompt. We are running the query 16, which is basically optional. Now you can see the result that we expected, that we have shown in the slide. The exact result is coming, right? There is no surprise, right? Now let us talk about the result of evaluating the left join with filter, right? So what we will be basically doing, we will be putting this filter on, right? So this is what we are doing. We are putting this filter on, right? So we have a situation where we have got a left join where the second part of the left join is having a filter with it, right? So let us see what output we will be getting, right? And then try to see how we can model that. So the result of output of left join with filter, we are having the same tables as input as we had in the earlier case, the simple left join. So here we are having all the elements that we had earlier, but we are also having one condition, one filter condition, right? The filter condition is that the birth of year should be equal to 1861. And if that is matching, that particular cell will be having the other value. But you see, for Paulo Coelho, which had a value to be 1947 in the simple left join, this is vanishing. So this is not there, right? So this is the result of the left join with the field for this particular case, right? So let us first check it out and then try to explain what is happening, right? So let us move to the command prompt. We have put on the filter condition, right? So yeah. So now you can see that the 1947 uh, entry has vanished from Paulo Coelho solution, right? Now the question is, how do we model this? So how do you define this formally, right? Now to define this formally, we make use of some other operator which we do not use, which we have not used directly, which is the def operator, right? So what this def operator is having, so this def operator is taking care of this filter thing. So it is taking into account the filter, right? Now we have got the same input, right? This M1 and M2, they are kind of same, right? And what does this diff operator do? This diff operator puts in the result as the solution which is not compatible. So this is one condition. The first condition is solution that is not compatible, right? So this is the first condition. So this first row, it aligns with this first condition. Now there is another condition. So even though a solution is compatible, even though the solution is compatible, so what are the solutions are compatible? This solution is compatible, this solution is compatible, and this solution this solution is compatible, this solution is compatible, and this solution is also compatible, right? But you see that Rabindranath Tagore has not appeared into this output or the result of evaluating D, right? So what is the condition? The condition is if compatible, then the so we are taking what? We are taking the mu1. We are not taking mu2. So this is mu1 and mu2. We are checking the compatibility with mu1 and mu2. But we are, as a result, we are taking mu1. Right? Right. Now, the second case, if compatible, then you see something that if you take the union of the solutions like Rabindranath Tagore, and then you take the union of this, what you will be having? Rabindranath Tagore string and 1861. So that is the result of union of mu1, mu2, right? And what would be the result of union of Paulo Coelho and this? It will be Paulo Coelho, which is kind of the URI, then Paulo Coelho, which is the string, then followed by 1947, right? And for Rabindranath Tagore, it would be Rabindranath Tagore URI, Rabindranath Tagore string, then 1861, right? And he will be having another one in English, the other for Hindi. I'm not writing the Hindi, right? Now, we will try to evaluate this union with respect to the filter, right? Whenever we'll be having a false, that particular mu1 will be going to your result set. Now let us check what I've said. So this is a solution. This is a union of the solution of mu1 and mu, which are compatible. But if you check this part of year is 1861, here we are failing. Here we are having a fail. So by this condition, this Paulo Coelho entry will be there as the outcome of D. So that is how we define the D operator, right? Now if you take the join of these two tables, we can do the join very easily. So we know what are the common elements like Paulo Coelho, we have a Paulo Coelho common. So we have 1947, Rabindranath Tagore is common, Rabindranath Tagore and Rabindranath Thakur is common. So these are kind of output of the join as we have defined earlier. Now we can see that if we apply a filter over this join, so filter over this join, and what is the filter condition? The filter condition is that B year should be equal to 1861, right? If that is so, then this particular row will be driven out from this evaluation of this filter result, right? Now what you have these two rows, which is you are applying a filter of this birth year equal to this over the join of these two tables, and you have the result of this diff, right? Now you check how these two is related to the left join. So this is basically the result of the diff, right? And this is basically the result of the filter over the join of say A1 and A2. You are applying the filter condition. So this is a kind of union of this, right? So that is how we can define the formal or you get the mathematical definition of the left join. So let us try to consolidate this, right? So how do you define the diff operator first? Let us define this diff operator. So you have got diff A1, A2, F. So diff is always defined with respect to a filter, right? So what would be our output? Our output would be always the solution from the first set, right? So you have mu I, right? And the multiplicity will also be from the first multiplicity of mu I in A1 or M1, right? So we have the solution set for A1 to be M1 and the solution set for A2 to be M2, right? Such that this mu I is there in M1, it belongs to M1, and for all mu j where your mu j belongs to M2, of course with multiplicity of mu j in M2 to be greater than 0. Now coming to the two conditions, either mu I and mu j are not compatible, right? Or we are coming to the union and then applying field, right? So let us first take union mu I union mu j. So this is your union of these two, and you apply filter over this, evaluate this over t, it should become false. In that case only you include mu y in the evaluation of diff, right? Now then how do you define left join? Simply the way we have presented in the last slide. You have A1, A2, F, the evaluation against G. So what we will be doing? We will be evaluating this expression. What is the expression? Filter the same F, and the filter would be the applied over the join of A1 and A2, right? Right? And you need to take union of this with the diff of A1, A2, F with respect to, right? So this is the case where we have two solutions and we have one filter which is attached to the second pattern, second graph, right? Now how do you convert this to have to work for the left join without any filter? Simply we just say left join, it is not joined, join, left join A1, A2, then true. So with this, I guess I have covered the definition, the formal definitions, and how do you really evaluate given a concrete data, different kind of expressions, right? So all these formalisms and other things, they have been taken from uh, in some way from this URL, where W3C, they have defined the semantics and meaning of the SPARQL construct, specifically considering the SPARQL 1.1. So for the details about what we have talked about, we can visit this URL. So thank you very much. This really ends the module of resource description framework. So in this module, we have discussed many things. The resource description framework itself, and how we can query one RDF data store using SPARQL queries, and then we have defined the semantics of the SPARQL, and we have evaluated the uh, SPARQL expressions or the algebraic expressions to see the result of query for a given data set. Thank you very much.